Hello guys, welcome to another episode of the FreeFEM series. After covering the basic concepts of 2D and 3D mesh generation as well as finite element spaces, in this video we want to talk about solving partial differential equations in FreeFEM. Let's go for it. So if you have followed Talks writers for a while, you know that this is not something that we have never discussed about. We have talked about this in a couple of videos, including the finite element series and also the theoretical videos about finite element concepts. But in this episode, I want to go through the details of various techniques that we can employ in order to solve partial differential equations in FreeFEM. And similar to the previous episodes, we have a couple of examples here that we go through them one by one, and we have also some documentations here. So I opened the folder in my text editor. And the first example is related to function approximation. As we discussed in the theories, like theory videos, function approximation is an important concept when it comes to numerical methods. And in this example, in the first example, we want to evaluate the efficiency of finite element approximation in FreeFEM by approximating a function, a continuous function f here, 2xy minus x squared, and we want to reproduce this function in a discrete space. And this discrete space is actually the mesh, the finite element mesh that we've produced, and then we map the function of f into that. Let's call the discretized function representation as u. In the end, after doing this, we evaluate the efficiency by computing the error. And in this case, this is a kind of L2 norm error that we compute in each node. These are the number of degrees of freedom, these are the concepts we have already covered. And then this error should be small enough. And then it shows that actually all the procedure and the process for function approximation is acceptable. The way we do it in finite element is, as you know, multiplying an arbitrary function. It is called test function. In this case, it is called v, to both sides of this equation. So uv equals fv, and then we integrate both sides, and after rearranging, we have this equation. So this is something that we can directly implement in FreeFEM. In this case, omega, because we integrate over the whole domain. And in this case, omega is actually the finite element mesh. And when we do this in FreeFEM, you can see actually where the power of freedom comes from, because you can directly input this into the FreeFEM script and then have control over various aspects of it. So here what we do in the example 1 is first defining the mesh. In this case, we use the square function, the number of elements in each edge, and then the size. As you know, we discussed this in the 2D mesh generation video. And then this is actually the function. We define f equals this, and then we plot the mesh. We define the finite element space, and this is the first order actually definition. First, we're using first order elements. We define two functions u and v, which are actually these two. And f is already defined here. And this is where the actual work happens. We say to FreeFEM that solve what follows. And the name of the, let's say, solve statement here is approx. We have u and v. We define a solver. I don't want to go to the details of this. I discuss it later. And then what you see here is exactly as this. So integration in 2D, because this is a 2D mesh. As I said here, we want to solve it and we want to map it to a 2D square mesh. And you see integration uv omega. So omega is the mesh here. uv minus, because we have moved everything to the left hand side, minus integration of fv over omega. So you can see integration 2D mesh fv. And that's it. When FreeFEM reaches here, it starts to run the script. When it reaches here, it solves this equation. This is not a partial differential equation, but it solves this statement and stores the solution in U. which is actually the first argument to that. And after doing that, we can plot U, and here U would be the discretized representation of F onto the finite element space. And then I compute the error. And error is also of type space P1. This is finite element space. And that's because we want to have it on each node actually. So the error is calculated for each node independently or separately, let's say, and then it is like computed as an integral, because this can be also represented as an integral. And then we print the error on the screen. So let's run this example together to see what happens. So I go to the example directory, FreeFEM example 1, and I want to turn off verbosity, and I run it. So this is the mesh. This is the number of degrees of freedom, and this is the final error. But before that, let's have a look at the function itself. This is the discrete representation of the function, and this is the error, which is very small, and it means that function approximation is performed correctly. And then, as we discussed in the theories video, and it is very trivial, if we increase the number of elements here, we should have a smaller error, because then we have a more accurate numerical representation, or in this case, function approximation of F. So let me run this with a smaller, let's say a finer mesh. This is a function. You can see that this is smoother and the error is very small this time. And so this was the first example. The second example, actually we did in the second, the third, and fourth, they are same problem, solving different techniques. And that's related actually to a stationary diffusion problem. It is formulated here, similar to the video that we discussed about a transient, a time-dependent diffusion problem. This is very similar to that, but we have removed the transient term. So the equation is like this. It has a second order derivative, because this is actually the divergence of a gradient, and then it becomes a second order derivative. It becomes a Laplacian, but this is a very general form. So the diffusion term equals F, and here I have repeated what we have discussed before. Just for easier access, we define a function, let's say a function space for test functions, which is defined like this, and then a function space for the trial function, which is actually the solution. And then the solution belongs to this one, the test function belongs to this. In FreeFEM, they are usually the same function space, like space P1 that we usually define. We multiply each term of the equation to V, becoming this, and then we integrate over the whole domain. Domain is the mesh in this case, the omega. And then we start to split this term, because this is not something that we can implement in FreeFEM. If you try to define this, FreeFEM gives you an error saying that I cannot deal with second order derivative. So we need to reduce it to first order. For doing that, we perform integration by part, and then for this term, we can use the Green's divergence theory to calculate that it is zero actually, because of the boundary condition. So using this theory, we convert the volume integral to a surface integral, and then we use the properties of the function space to say that it is zero. So we can say that actually this term equals this one. And this is what happened here. And then we substitute equations and we rearrange it. And then this is actually the final form of the weak formulation of the equation. And this is actually something that we can directly input in FreeFEM. So let's have a look at the example. We have a definition of a mesh. In this case, we use the parametric definition of geometries. We have C1 as a value that we want to pass to the internal boundary. So this is actually, a circle that has an internal square. And because the square has 4 edges, we need to have a label assigned to all of them, because we want to assign the same boundary condition to all edges. And then for this one, we use C0 later on when we want to define the boundary conditions, because it is only one boundary. We then define a mesh, we plot a mesh, you can see the mesh soon, and then the finite element space. defining the u and the v that belong to the same space P1, as you can see here. And then f is also of the type space P1 because it can vary from node to node or from element to element. As you can see here, I have said try 10 times x, and then you see that, the f varies from node to node. And then similar to what we had in the function approximation example, we say solved. In this case, it is diffuse. The name doesn't matter at all, u and v. And then here is actually what you see here for the first term, so bringing d out of this, and then we have the gradient of v multiplied by gradient of u. We can also use macros, as you can see later on in one of the examples. You can define macros for doing this, but this is a very raw definition according to, vector calculus. So this is the first term, and then we say minus fv. So this is this one, integration over the whole domain. And then we want to define the boundary conditions, like we see on C0, which is the name of this boundary, on the surrounding circle, u equals 20. And on C1, which is defined here, and that's actually the label that we have assigned to all the edges, on C1, u equals 60. As simple as that. And yeah, this is really amazing that how simply you can define the weak formulation here and then solve it using the solve keyword. And after solving that, the solution is stored in U and we plot it. So let's run the second example to see how it works. And this is the mesh. We plot using this command. And then I press enter. And this is actually the solution of the stationary diffusion problem, assigning 60, as you can see in the values, to the internal obstacle or internal hole or internal boundary, and then to the outside, to the circumstance, it is 20. And yeah, as I said here, you can try different values for f. So let me run this one, and then you see that actually this is a different solution. And I press M, this is the mesh. You can try different numbers, and you see that, yeah, the solution will be smoother. Okay, and then for the third example, actually the third and the second example are the same, so very similar, but with a minor difference. And you can see that, yeah, I open the third example, you see that this example, the second and third, are exactly the same, except, yeah, I've changed this one. And then the only difference is actually here we have the solve keyword, and here we have problem. And the problem is actually kind of function definition, let's say, that when you define a function in a programming language, it doesn't run until you call it. And this is the same. We define diffuse as a problem, but FreeFEM doesn't solve it when it reaches here. Instead, we need to call it whenever we like. Like in this case, I called it immediately after the problem definition, but it can be called elsewhere, like inside a loop or inside a conditional statement or whatsoever. So that's actually another type of definition in problem, like for partial differential equations for the weak form implementation in FreeFEM, and the solution would be exactly the same. There is no difference at all. So I run example 3, and you see that we end up with the same solution. And in addition to this, there is another way of defining this system, this weak formulation and a solution of the PDE. And that's actually the method that I use a lot, and you will see this a lot in Tux writers, because this gives you even more control on the definition of the linear system. So in this case, you can assemble the linear system yourself. So like the definition, like we discussed this before in the theory videos, that in the end, this equation is converted to a linear system of equations ax equals b, and we are looking for x. And in this case, for example 4, we solve the same system, and instead of using problem and solve, we want to assemble the system ourselves and then solve it using, some of the solvers available. And later on, we can pass it to some high performance computing libraries in order to improve the performance. And as I said, we have more control on various aspects of the solution and the solver. So in this case, you can see that we have everything is the same, except we need x here, a new definition here, which is actually the real x we are looking for. So ax equals b. That x is defined here as the space P1. In type of space V1, we have f defined. And then you see here varf. And varf has, a fundamental difference to problem and solve. As you can see here in problem and solve, we have a negative sign here for the second derivative, for the second integration. And in this case, it is positive. And the reason is when you need to refer to this theory and also the theory guide that we had before. But the thing is, instead of using this form, we need to use this one. And the reason behind it is because we want to assemble ax equals b, and a comes from here and b from here. And it means that the signs should be correct. When we are talking about the right-hand side is actually a positive integration as well as the left-hand side. But in this form, like in example 2 and 3, that's negative. And in example 4, we define it as positive sign. So actually, all the terms appear in the var form statement with the original sign without rearranging. This is very important. And then we have the definition of a boundary condition. So everything else is the same. And then we have the definition of a matrix A and an array B, which has a size of a space P1 degrees of freedom. Please refer to the theory video if you are lost here, sort of. And then we define, we calculate A and B by calling diffuse, which was the name of the varf statement. For A, we say this is the bilinear term, space B1, space B1. And then for B, this is the linear term that is calculated from the right-hand side with U, with the trial function being 0, because we don't have any trial function in the linear term. These are the things. If these are complicated, please refer to the video, to the theory video. We had all you need to know from the finite element theory in 3 videos already discussed in Talks Writers. And then x can be calculated as simple as this. And this is actually something that is automatically done by FreeFEM. And yeah, here it's where we can have more control on the solution of things. Later on, you will see we do it with high performance computing libraries and preconditioners and stuff. And then we plot x, because this time x is actually the solution and not u or something else, because u doesn't exist outside of the varf statement. And that's why we didn't define u and v here, because we are only seeking for the value of x. And then I run this example 4, and the solution is exactly the same. So this is very important to know the difference between these 3. And the last example is very similar, but it's related to solving the equation on a surface on, let's say, a 2D geometry in 3D space. So it defines a surface using this is something we already discussed in the mesh generation video with a square tree function, which has a type of mesh S. And then we define the finite element space on this surface mesh with P1. We define U and V. And then we have this solve statement here, meaning that FreeFEM solves it when it reaches here and stores the solution in U. And as you can see, it is 2D on the surface mesh. This is actually a donut-like mesh. You will see it. And then this is the definition of the same equation that we solved. So this is actually f. So f equals x plus y multiplied by v. Everything moved to the left hand side. And then here, instead of defining the bilinear form like this, we have defined a macro here that is called grad 3. And then here we have the transpose of it times the gradient itself, implying that it will be like this in the end. So this is really for simplifying the notation in FreeFEM. And yeah, this is very common to write it like this. And then after that, we plot U and we see how it works. So let me run it. And this is the donut, and then the equation, the Laplace equation, being solved on this mesh, which is actually a surface and not a volume mesh. Okay, so yeah, this is what we wanted to discuss in this video about various techniques to solve partial differential equations. You see, various forms, all these three in various examples of FreeFEM in the documentation and codes that people share. And it's very important to know the differences. As I said, the most important difference is actually the rearrangement that is needed in these two, and not when you wanna solve it using a varf statement. I hope you find this video useful. See you in next videos. Bye.